Sir, you can start.
Okay, thank you very much for inviting me. And it has been a while since I've been in India. Before Corona, I used to visit India at least 7 to 8 times in a year. In fact, one time I told them I should get Indian citizenship. Uh, Anyway, it's good to see all of you, and I see uh, my co-editor in the journal here too. This is a talk uh, maybe in 1997, or I mean this paper, or 1998, and I never spoke about it in a conference. It's about characterization of valuation domain using m-canonical ideals. Okay, as usual, we let R be an integral domain with a quotient field K. What do we mean with a fractional ideal of R? A fractional ideal of R is an R submodulo I of K such that there exists a non-zero R in R such that Ri will put you inside R. So fractional ideal, you think of from the name, like if you think of Z, the integers, and you think the quotient field is a Q, then the ideal generated, if you take 1/3 as Z modulo, you know what I mean with that. Like you take the span of 1/3 over Z. This is definitely a Z submodulo. And of course, your R here will be 3. If you multiply 3 with 1 over 3, you know, you get everything inside R. So you need to know what we mean with the fractional ideal. Is nothing but an R submodulo, we call it I or whatever, and there is a non-zero R where Ri put you inside R. Okay, if T and W are a fractional ideal of R, then what do we mean with this notation? T colon W. It means all the element in the quotient field K, X in K. Remember, K is the quotient field of R, where XW inside T. It depends on, some algebraists, they do it the other way around, like XT in W. But here I stick with what's written in the paper, the elements in K where XW is in T. Okay, so what do we mean with m-canonical ideal? If you have a non-zero ideal I of R, a non-zero ideal, and remember that R is integral domain. And remind you, integral domain meaning commutative ring, but 0 is the only zero divisor. If this condition hold for every non-zero ideal L of R, you take I colon, definitely I colon L does not need to be in R. Remember, uh, this could be in K. Okay? And it could be in I, because I colon L mean all the elements in K where XL is in I. Okay? And then you do it again with I, if you look at the notation. So I colon L will be a fractional ideal. And then you use the definition again and you come up with L. And you want this to be true for every non-zero ideal L of R. Of course, I don't have to remind you, but it's clear from the definition that every proper ideal of R is a fractional ideal, but definitely not every fractional ideal of R is a proper ideal of R. Okay, this type of ideals is studied by well-known algebraist, commutative algebra, Heinzer. I think all of you know the name. And then Barocci or Barocchi, I think Italian, Barocci, I think. And there is other related studies in past 1963, Bazzoni and Salci, Herzog, Kans, Houston, Zafrallah, Matlis, Nagata, Olberding, and uh, I cannot pronounce the name. I know him, Vazonis. Sorry, you see the name. Okay. So first thing, let me remind you again, like if you take span, if you take your ring R to be Z, for example, okay, then if you take the span of 2/3 over Z, this is what we call a fractional ideal, okay? If you go back to the definition. All right. This notation here, what do I mean with Rm? This is abbreviation. What I'm saying here, R is integral domain with exactly one maximal ideal M. If if you have an integral domain with exactly one maximal ideal and admit proper radical m-canonical ideal, so my m-canonical ideal is radical, then I has to be a maximal ideal of R. Well, what's that mean? That means it has to be M because it has only one maximal ideal. So what that mean in using simple language, which I call it street language, uh, the radical m-canonical ideal of such domain just M. Okay? All right. Uh, Again, the same notation. R is integral domain with maximal ideal M. A quasi-local domain. Quasi-local domain is just what I told you. Uh, Integral domain with exactly one maximal ideal. Then R is a valuation domain if and only if R admit a proper m-canonical ideal I such that I colon M is a principal ideal of R. And let me remind you what we mean with valuation domain. There are many definitions. The easiest one is maybe the one you know. If you have two elements in the ring R, let's call them A, B, then A has to be a factor of B or B has to be a factor of A. For if your ring is not integral domain and you have the condition where A is a factor of B or B is a factor of A for every A and B in R, then another name is a chain ring. But for integral domain, we use valuation domain because there are other definition using, valuation. But I think I like the simplest definition. So this is like a complete characterization of valuation, and it is known that valuation domain quasi-local, meaning every valuation domain has exactly one maximal ideal. So this is one way, one characterization of valuation domain. An integral domain is a valuation domain if and only if R admit a proper m-canonical ideal where I colon M is a principal ideal of R. So what that mean? That mean this one here, remember the definition of I colon M is all the elements like X in K, where K is the quotient field of R, where XM in I. So that mean the only element where XM in I, they have to be in R, because I'm saying it is a principal ideal of R. All right, so this thing here has to be lives inside R. Okay, so maybe you see now why I'm assuming always that my ring has exactly one maximal ideal, because valuation domain, they only have one maximal ideal. Here is another characterization. If you have a quasi-local domain, and R, then R is a valuation domain if and only if R admit a divided proper m-canonical ideal. This is if and only if. So you're gonna ask me what do I mean with proper, with divided? Well, if you have a prime ideal, uh, if you have uh, an ideal I, we call it divided if whenever you choose an element outside I, let's say X, then X has to be a factor of each element in I. Okay, so this is divided. Divided mean I is divided, meaning whenever you select an element outside I, then this element is a factor uh, of uh, of each element in I. Okay, all these just characterization of when a quasi-local domain is a valuation domain in terms of m-canonical ideal. Here is another result. So if you have a quasi-local domain with maximal ideal M, then R is a valuation domain if and only if Cm is m-canonical ideal of R for some non-zero C in M, C in R. Okay, so these are the if and only if. Okay, the next theorem is kind of maybe interesting. So if you have a valuation, if you have a quasi-local domain, And let's assume your R is a valuation domain. Can you give me all m-canonical ideal? Yes, they are described in this result. They look like, all of them, they look like Cm, where C is a non-zero element of M. So we have a complete description of m-canonical ideals inside valuation domain. And this is a complete characterization we have here. Okay, in fact, since we started late, maybe my talk is going to be short. Uh, this is my last result on value on characterization of valuation domain. Uh, Here is it. If you have a quasi-local domain with maximal ideal M, then R is a valuation domain if and only if M colon M is equal to R and R admit a proper M canonical ideal where I colon M is finitely generated ideal of R. Okay, this paper published, as I told you, maybe 96, 97 in Communication in Algebra. If you are interested, I have the paper. You can write to me and I will be happy to send it to you. I just decide there are some examples and other definition, each local, divisorial, and other things. They are, I decide not to include it here. I just want to give you an idea on this m-canonical ideal. And I have a question. If some of you familiar with that, it just came to me today when I was preparing the talk. Uh, there is other class of domain. They call it pseudo valuation domain. Every valuation domain is pseudo valuation domain, but not every pseudo valuation domain is valuation domain. And this class of pseudo valuation domain introduced in the 70s by Houston and Hedstrom. Uh, and they've been studied by many, including myself, the pseudo valuation domain. I was thinking, can we characterize them using m-canonical ideal? I have not seen this kind of work, characterizing pseudo valuation domain using m-canonical ideal. Or maybe my question is trivial. I just crossed my mind as I told you when I was preparing this talk. I did not, but that's kind of interesting to me. And of course, since you do it for valuation, can you do it for a proofer? Because proofer domain, we know one of the characterization that localizing R at every maximal ideal is a valuation domain. This is one characterization of a proofer domain. An integral domain is a proofer domain if and only if R localized at M, where M is a maximal ideal, is a valuation domain. Uh, I'm not sure if somebody did that. Maybe they did. I'm not aware of it. These kind of a question came to me, or can we generalize this concept? Because I have not seen many papers on m-canonical ideals. Maybe I saw uh, five, six, or maybe less than that. So this concept has not been studied uh, extensively, or maybe they did, but I don't think so. I would know about this concept, even though, as I told you, I mean, well-known algebraists studied this class of Heinzer and others, and Muhammad Zafrallah and others, you know. Anyway, so I believe for if there is a graduate student sitting there doing master or something, maybe they want to look up this uh, concept, m-canonical ideal, and see whether they can generalize the concept or they try to characterize other class of rings using this kind of ideals. Okay, I think that's good enough for me, and I thank you again, and I'm done.
Okay. Anybody has any question to ask? Any clarification or anything?